Welcome back to the Deep Dive. For thousands of years, we've stared up at the stars, just completely mesmerized, wondering what's out there. But we're way past just wondering now, aren't we? We are
Mm.
actively exploring, driven by this innate human need to push boundaries. Today, we're going on a pretty amazing journey, diving deep into the European Space Agency, or ESA, and their incredible science missions. We're talking about missions that span from, well, the very heart of our sun, right out to the edge of everything we can see. And our goal here is simple. Give you the shortcut, the fast track to being really informed about how ESA is trying to unlock these huge cosmic secrets. Where did we come from? How did the universe evolve? Expect some surprising facts and some real aha moments along the way.
Yeah, and that's the really cool part. I think these aren't just, random shots in the dark. When you look at the whole program, you see how each mission, each piece of data, it feeds into this much bigger story. We're not just gathering facts, we're genuinely trying to piece together the fundamental story of, well, everything, how it all began, how it changed, and how we ended up here.
Okay, let's unpack this then. Our journey has to start right at the center, doesn't it? Our own sun. I mean, this star affects everything on Earth, our climate, our technology. So understanding it is, well, it's critical.
Yeah.
And surprisingly tricky.
Oh, absolutely. And what's fascinating is how each mission sort of builds on the last. You take Ulysses, for example. That was ESA's first big heliophysics mission studying the sun's physics. And it gave us this totally unique viewpoint. It actually flew over the sun's poles. Before Ulysses, we mostly thought about the solar wind and magnetic fields in, 2D. Ulysses showed us the 3D nature of it all. It was like getting the first proper weather map for the whole sun. A huge leap.
Right. And then ESO came along and just, wow, completely revolutionized space weather science. It's constantly sending back these incredible images of solar flares and eruptions, which is vital for predicting space weather that could, knock out satellites or power grids. But it also made this completely unexpected discovery, didn't it? Thousands of comets.
Exactly. Thousands of sun-grazing comets. Imagine that a solar observatory suddenly becomes this amazing comet hunter. It showed us these icy bodies just plunging into the sun. Amazing.
And now we have Solar Orbiter, getting closer than any European mission before, looking at the sun in just unprecedented detail. It's watching flares, big explosions, and even these little mysterious bright spots they're calling campfires.
Yeah, those campfires are really intriguing. They're tiny compared to flares, but there are loads of them. And the thinking is maybe, just maybe, these small events collectively could explain why the sun's outer atmosphere, the corona, is millions of degrees hotter than the surface. It's a long-standing puzzle.
That would be huge if they figured that out. And it's not just the sun in isolation, is it? It's about how it affects us here on Earth. That's where missions like Cluster come in, and the upcoming SMILE mission, too.
Precisely. Cluster's been fantastic for understanding how solar storms interact with Earth's magnetic shield, our magnetosphere. Knowing that is crucial for protecting, well, everything in orbit, and even systems down here.
So SMILE is going to take that even further.
Exactly. SMILE is designed specifically to get a more complete picture of that Sun-Earth connection. It will measure the solar wind directly and watch how it dynamically interacts with our magnetosphere. So altogether, these missions give us amazing insights and help us prepare for, the sun's more dramatic moods.
Okay, so we've looked at our star. Now let's journey outwards to the planets. This is where it gets really interesting, I think. What can these neighbors tell us about Earth and about ourselves? Why did they turn out so differently?
It's the big question, isn't it? And these missions are genuinely changing how we see our cosmic neighborhood. Take Bepi Colombo. That's Europe's first mission heading to Mercury right now. It's arguably the least explored rocky planet. Just getting there is tough, fighting the sun's gravity and heat. But the goal is to study everything, its inside, surface, atmosphere, magnetic field, to figure out its origins and why it's so, well, dense and iron-rich.
A real challenge.
Yeah.
And then there's Venus, our quote-unquote sister planet. Venus Express showed us just how different it is, those extreme winds, the runaway greenhouse effect. It's kind of a cautionary tale, isn't it?
It really is. And the upcoming Envision mission aims to dig much deeper. It's going to give us a complete view of Venus from its core right up to the top of its atmosphere. The key question is, how and why did Venus and Earth evolve so differently? Was it always fated to be this hellscape, or did something specific happen? Understanding that divergence is crucial for planetary science in general.
And meanwhile, Mars Express is still going strong at the red planet, right?
Yeah.
Still looking for signs of past life.
Still plugging away, yes. Continuously searching for more clues about potential past habitability, looking for evidence of ancient water, maybe even environments where life could have once existed.
Okay, let's go further out now into the outer solar system. JUICE, that's the Jupiter mission, heading for the icy moons.
That's the one. An incredible feat of engineering. It's powered by these enormous solar arrays, like the size of tennis courts. They had to perfect them for deep space where sunlight is incredibly weak.
And its main goal is those moons, Europa, Ganymede, Callisto.
Primarily, yes. Detailed looks at Jupiter, too, but the big focus is assessing the habitability potential of those large, icy satellites. We think they have vast oceans under their icy shells. Could something be living in them? JUICE is going to give us our best look yet.
And didn't ESA land a probe on Titan, Saturn's moon, years ago?
They did. The Huygens probe, part of the Cassini mission. A huge success, the first landing in the outer solar system. And building on that kind of ambition, future plans are looking towards Enceladus, another of Saturn's moons. It's small, but fascinating because it's spewing geysers of water and organic stuff from its subsurface ocean.
Ah.
Yeah, so it has immense potential for life beyond Earth. It's a prime target for the Voyage 2050 program, searching directly for signs of habitability.
It's amazing. Okay, from giant planets and icy moons to, well, the smaller stuff. Comets. You called them cosmic time capsules earlier.
I think that's a great way to put it. And missions like Rosetta really let us open them up. Rosetta didn't just fly by. It orbited Comet 67P for years and landed the Philae probe on it. That was groundbreaking.
I remember watching that landing. Incredible.
It gave us such detailed information about the comet's surface, what it's made of, how it changes as it nears the sun. We learned they're not just dirty snowballs, but complex, active worlds with, crucially, lots of organic molecules, the building blocks of life.
And now Comet Interceptor is going to look at a different kind of comet.
Exactly. This will be the first mission to visit a truly pristine comet, one that's potentially making its very first trip in from the Oort cloud, the outermost edge of the solar system. It hasn't been processed by the sun repeatedly, so it's like getting a sample of the original stuff our solar system formed from.
A direct look at the ingredients for planets and maybe life.
That's the hope. Connecting the dots, Rosetta and Comet Interceptor are really unlocking the secrets of these ancient objects, telling us about the early solar system and maybe even how life's ingredients got to Earth.
Okay, we've toured our solar system. Time to zoom out further, beyond our neighborhood, to the hunt for exoplanets' worlds orbiting other stars. This is where the question, are we alone, really comes into play, isn't it?
It really does. And what's fascinating is the methodical approach ESA is taking. Each mission builds on the last, refining our search. Take Cheops. It was the first mission designed to precisely measure the size of known exoplanets.
Why is just the size so important?
Well, if you know the size accurately and you can estimate the mass from ground-based observations or other methods, you can calculate the density. And density tells you a lot about what the planet might be made of: rock, gas, water. Cheops found some really weird planets, challenging our ideas about how they form. Planets as big as Neptune, but light as styrofoam, things like that.
Huh. Weird. So Cheops measures known planets. What's next?
Plato. Plato's mission is different. It will survey lots of bright stars, specifically looking to discover Earth-like planets orbiting Sun-like stars. And crucially, it's focusing on planets in the habitable zone, the region where liquid water could potentially exist on the surface. It's a targeted search for Earth's cousins, you could say.
Finding potential Earths. And then
Ariel. Ariel takes the vital next step, analyzing the atmospheres of these exoplanets. Finding them is one thing, understanding them is another. Ariel will carry out a chemical census, looking for molecules like water vapor, methane, carbon dioxide. It's searching for clues about how these planets formed and whether they have the right ingredients, chemically speaking, to potentially support life.
a chemical census of alien atmospheres. That sounds like pure science fiction, but it's happening.
It's incredible, isn't it? The systematic approach is bringing us closer and closer to understanding worlds beyond our own.
Okay, so we've gone from our sun to our planets to other solar systems. Let's go bigger still. Mapping the entire universe. Becoming like cosmic cartographers.
That's a great description. And you have to ask, how do you even start mapping the cosmos? How do you trace its history? It really stands on the shoulders of earlier missions, like the PACOS, which was ESA's pioneer in astrometry, precisely measuring star positions and movements. It gave us accurate distances. And then Planck, which mapped the oldest light in the universe, the cosmic microwave background radiation, the afterglow of the Big Bang. These really laid the foundations for modern cosmology.
Right, setting the stage. And then Gaia came along.
Oh, Gaia has been an absolute game changer. It's created this mind-blowing billion-star map of our Milky Way galaxy. It's the largest, most precise 3D map ever made. We can see the structure, the history, the movements of stars within our galaxy like never before.
What kind of things has it shown us?
All sorts. It's revealed how the Milky Way has grown over billions of years by merging with, well, basically eating smaller dwarf galaxies. Galactic cannibalism. It shows our galaxy is much more dynamic than we perhaps thought.
Wow. And going beyond our galaxy.
That's Euclid. Euclid is now mapping billions of galaxies across vast stretches of the universe. Its main goal is to tackle the big mysteries: dark matter and dark energy. These make up about 95% of the universe, but we can't directly see them.
So how does mapping galaxies help with that?
Because the way galaxies are distributed, how they cluster together, is shaped by the gravity of dark matter pulling them together and the push of dark energy accelerating the expansion of the universe. By mapping billions of galaxies over cosmic time, Euclid can trace the history of this expansion and the growth of structure, giving us crucial clues about what dark matter and dark energy actually are.
It's staggering to think about mapping billions of anything, let alone galaxies. And so much of the universe is hidden from our eyes, isn't it? We need different kinds of vision.
Exactly. We need to look beyond visible light. And that's where ESA's observatories covering other parts of the electromagnetic spectrum come in. What's really cool here is how these missions let us see through dust, peer into cold regions, or detect extreme heat and violence. They show us how complexity builds up in the universe, from gas clouds to stars to galaxies, and reveal the chemical makeup of it all.
Like the infrared telescopes.
Right. ESA was the world's first orbiting infrared observatory, a real pathfinder. It opened up the cold universe, things hidden by dust. That paved the way for Herschel, which observed in the far infrared and gave us spectacular views of star-forming clouds, stellar nurseries, and tracked how galaxies evolve over time.
And at the other end of the scale, the really high-energy stuff.
Yep. Integral looks at gamma rays. These are produced by the most energetic events. Think black holes feeding, neutron stars colliding, massive stars exploding as supernovae. Integral gives us a unique window into that extreme physics.
Then there are X-rays too, right?
Absolutely. XMM Newton has been a workhorse in X-ray astronomy for decades, making countless discoveries. And its successor, New Athena, is set to be revolutionary. A next-generation X-ray telescope designed to transform our understanding of the hot and violent universe.
How will it do that?
It will map out vast structures of hot gas that permeate galaxy clusters, determine their properties, and hunt for supermassive black holes, especially the elusive ones in the early universe. It's tracing how the ordinary matter we're made of actually assembled into the structures we see today.
And you mentioned Archimedes. What's its angle?
Archimedes is interesting. It's designed to look for extremely faint whispers of light, specifically the diffuse, low-surface brightness structures around galaxies. It's trying to find the remnants of past mergers, faint dwarf galaxies, basically, revealing the hidden structures in the dark parts of the universe, adding another layer to the picture.
It really does feel like we're developing entirely new senses to perceive the cosmos, which brings us, I guess, to the newest sense of all, listening to the universe through gravitational waves.
This is genuinely a new era in astronomy. It's like we've only ever had cosmic eyes, and now we're getting cosmic ears. It lets us detect events that are completely invisible to traditional telescopes, adding a whole new dimension.
And LISA Pathfinder was the test for this.
Exactly. It was absolutely crucial. LISA Pathfinder brilliantly demonstrated the technology needed to detect these incredibly faint ripples in space-time from space. It proved you could isolate test masses, basically perfectly still cubes of metal in free fall so precisely that only a passing gravitational wave would disturb them. And it tested the ultra-precise lasers needed to measure the minuscule changes in distance between them. It proved the concept works beautifully.
So the stage is set for the main event, LISA.
That's right. LISA will be the first space-based gravitational wave observatory, a constellation of 3 spacecraft millions of kilometers apart, connected by lasers. It will be able to detect gravitational waves from enormous events across the universe, merging supermassive black holes in the centers of galaxies, pairs of compact stars spiraling into each other, maybe even echoes from the very early universe.
Listening to black holes collide, it's just mind-bending stuff.
It truly is a completely new way to explore the cosmos.
Wow. Okay, deep breath. From the sun's surface campfires all the way out to listening for space-time ripples. And stopping off at planets, comets, exoplanets, and galaxies along the way. We have covered an incredible amount of ground, or maybe space. You, our listener, just got the ultimate shortcut to understanding the sheer breadth and depth of ESA's cosmic exploration efforts.
And it's so important to see it as this ongoing collective journey, isn't it? Each mission builds on the last, answers some questions, but always raises new ones. It creates this legacy of exploration that inspires the next generation of scientists, engineers, well, dreamers, really, to keep pushing outwards.
Absolutely. So what does all this mean for you listening right now? Well, it means our picture of the universe and our place within it is constantly being redrawn, refined, made richer. These aren't just abstract scientific projects happening out there. They fundamentally connect back to us, to our understanding of existence on this small blue planet. And maybe here's something to think about as you go about your day. Considering everything we've touched on, from potentially understanding the sun's heating mystery with tiny campfires, to charting billions of galaxies, to probe dark energy, to actually listening to black holes merge, how might these discoveries, as they continue to unfold, fundamentally reshape not just science, but maybe our whole philosophical view on life, the universe, and, well, everything? Keep looking up, keep asking questions, and keep diving deep with us.